All right, Aisha. So there's some stuff in his notes that are not exactly correct. For example, H0 is the null hypothesis. My students call this the status quo. It is what you expect when there's no difference between something that you're comparing. You're usually comparing things. HA is alternative hypothesis, and he said something in his notes that you always want to find out if whatever you have is different than the null hypothesis. That's not necessarily true. Sometimes you want to not find that out. Maybe you want to say that a test has breast cancer. You want to actually have it be H0, select H0. So in each of these, the goal is to determine if you have enough statistical support to reject the null hypothesis. So for example, one of the examples, and I'll pull it up so you can see it, is men's performance and women's performance different? And we can just take a look at the picture on different physical tests. Now, you would think so. You think, oh, of course they're different. But to prove it, you would actually need to have some statistical evidence for that. So let me pull one. So for here, I'm going to show you a picture of this. There's what we call the eyeball test, and you can see it here. Make this bigger. Pull this out. So these are push-ups, and what you're looking at is different cluster groups. So this is a comparison between group 1 and 2, and is there a difference in their mean values? And you see it's slightly, this mean is slightly above 0, so it doesn't look like there's a difference with the eyeballs. On number 2, it's group 1 and 3, and the difference between the means, the average difference between the means is around 20-some push-ups. So you, with your eyeballs, would say, of course, it looks like there is a difference between groups 1 and 3. This isn't male, female, these are groups. So in these groups of people doing push-ups, I would, with the eyeballs, let's say they weren't colored, but with my eyeballs, I would say, well, it looks like there's a difference between the two. However, I need to actually prove that because I don't know that for sure. And that's what statistical tests do. They give you statistical support. It's not a proof, but statistical support, which could be wrong. It always could be wrong. All these teal ones, there was a true difference. If you look at 2 to 3, 2 to 4, there might be an eyeball difference. There was a difference in about average of 5 push-ups. How about this one over here? This is 4 to 5. The difference was, the average difference was 18 push-ups. You can kind of see it from here. Well, 18 push-ups is pretty high. So with my eyeballs, I would say that actually does look like there's a difference. When we applied the statistical test, it turned out there wasn't a difference. So that's what statistical tests do. They prove or verify for you or provide that statistical support so that it tells you whether there's a true difference or not. So there was a experiment that they ran in class where undergraduates listened to a song and guessed the length. The actual song length was 10 seconds. So we know the true value of what the actual song was. And when people guessed how long the song was by what they weren't given a watch, they guessed around average of 13.7 seconds. So the question is the guess of the length of the song actually the length of the song? Is there really no statistical difference between these two? So how do I set up the null hypothesis? I always have to use symbols. So my null hypothesis here is the status quo. The status quo is that everybody got it right. So the length of the song is 10 seconds. They estimated correctly. Now, if they didn't estimate correctly, my alternate would be that the length of the song is not 10 seconds. They over or underestimate it. Now, you could say, well, I don't think they're going to underestimate. I'm going to always think they're going to overestimate. If you say that, this alternate hypothesis set by you would be mu is bigger than 10, and you would do a right-sided or right-tailed test to do that. And he has that in his notes because you're only interested in more than. I'll give you another example. If you think men can do more push-ups than women, the null hypothesis would be that men and women are equal. The number of push-ups that men do and the number of push-ups that women do are equal. And the alternate hypothesis would be that you think men can do more than women. So it would be an inequality. I need to make a choice somehow with some kind of analysis that whether it's H0 or HA. So to do this, I need to find out if that sample is different than the null distribution. And the way they did it in class is they actually simulated distributions, but I'm just going to run you to the picture. So here is the actual, what the mean of the sample was, and this is the distribution with guesses if they were randomly guessing around, if they were making random guesses. And you want to ask yourself if it's possible that this mean is not the status quo. And it looks like from the eyeballs that it isn't. Like, how could they possibly have got to the top of this distribution when the random distribution looks so, they're not making a random decision. They're actually overestimating it. So the p-value is the area under the curve. It's not really, but it's close enough to think of like that. This area under this curve right here, that's to the right of this line, and to the left of whatever line that, if you want to do two-tailed here, should be close to 0. And so the smaller that to the right is, the more likely that they're further, that it's the alternate hypothesis, because it's unlikely that you'll be that far away from the mean. So you don't need to see this. So this is the type 1 and type 2 error. I think of this as predictions. So I'm going to use predictions based off the data, whether it's calculating the mean, whatever it is, I'm going to do a prediction. And what actually is true, I don't really know that, but there's something that's actually true. Now, what could happen? I could say that my prediction could be that the null hypothesis is not true, but indeed the null hypothesis was true. So that's an error because I predicted that the null hypothesis was false when it was actually true. That's called a type 1 error. And it's different than a type 2 because what you've done is, let's say it's breast cancer. I have a diagnostic test, and this diagnostic test tells me the person has, I want to make a diagnosis and say that the person has breast cancer. Well, the status quo would be that no one has breast cancer. And if I say that, so the fact is they don't have breast cancer, I said that they did have breast cancer, that's called a type 1 error. On the other hand, if I say that H0 is true when it was really false, they didn't have breast cancer, but they actually did, that's a type 2 error. And the other two are the actual correct things. And you want to pick your statistical test so that it ends up being correct probably. Alpha is what we call the probability of making a type 1 error. And typically alpha, you want alpha to be low. For science, we set it usually at alpha equals 0.05. You also see 0.01. So there's other values people choose, but nobody chooses alpha equals 0.9. They want it to be pretty low. You don't want to make that error. Beta is the probability of making a type 2 error. You also want that to be low. We don't use beta, we use 1 minus beta. It's called statistical power. So you want 1 minus beta to be high, which is negative. So what we usually accept is 0.8. For 1 minus beta is power of 0.8. I pulled this from a table that I got from a book. So you see those things, type 1 and type 2. So here I said they had breast cancer when they really didn't. That's a false alarm. Over here, I said they didn't have breast cancer when they really did, which is also bad. So either one of these errors, depending, would be bad. Now, let's suppose I was going to send report cards home based off of your, I'm guessing how much your body fat you have. And I'm going to send a body fat report card home. Well, if I make an error there and say you're too fat when you're not, that could actually have large repercussions. So in that case, type 1 error is really bad. You'd be more comfortable to type 2 error saying they're not fat when they really are, because they would have the shame of having that report card. So these two things are not sometimes equally bad. It depends on the situation. This was something let me see if this was interesting for you. Yeah, I mentioned this before. This was something I did with my students. I said, okay, let's suppose, they actually have done these tests where can you actually sense when someone's standing behind you? And so how would we prove someone has the ability to sense when someone's standing behind them? Do you have to, like, what percentage out of 10 times that you stand behind the person can they actually sense it correctly? What would you be comfortable with? A parameter is the number of times that you actually stood behind the person. So that's the actual true mean. A parameter never changes. It's the true thing. A statistic is dependent on your sample, how many times you got it right when you ran it 10 times. So what would it take you to convince? If in this case it was plebes, like if a plebe got it right 9 times out of 10 that they were sensed, would you be convinced? Maybe not. So the evidence that you would need might be stronger for something like this. You always want to statistically show that the plebe guesses can be explained by chance. You want to know if the null hypothesis would be status quo. The plebe guesses could be explained by chance alone. The alternative would be that the plebe's guesses could not be explained by chance alone. So it's not the status quo. So these are just some things. I'll send these slides to you. They're good slides to just look over. Okay, so I'm going to send these to you. But it gives you an idea of how this works. I think these answers all your questions. You wanted to see an example. Here it is. And how to calculate these things. I can show you some of that if you want to see some how to do these calculations.